For decades, predicting the weather has been a brute force mathematical exercise, but a new computational approach is quietly challenging that dominance. The primary tool for traditional prediction is the High-Resolution Model, or HRES, run by the European Center for Medium-Range Weather Forecasts. HRES relies on what climate scientists call the standard approach. It is deterministic, meaning it explicitly simulates the atmosphere by calculating fundamental thermodynamic laws and Navier-Stokes fluid dynamics. Recently, pure artificial intelligence models have entered the space, such as Google's GraphCast and Alibaba's Fuxi, built entirely on graph neural networks and transformers. These architectures do not calculate fluid dynamics, and they possess no hard-coded physical laws. They operate entirely by mapping spatial and temporal relationships across billions of historical data points. When measured against standard evaluation benchmarks, these pure pattern recognition engines are consistently achieving lower error rates than the traditional physics-based models. This creates a deep structural tension in climate science, a high-stakes competition between explicit physical equations and implicit data-driven computation. To evaluate these models, we must look at their fuel source, an archive known as ERA5. ERA5 is a massive reanalysis dataset. It maps global weather observations across a tight latitude-longitude grid, spanning from 1979 to the present. Every spatial relationship and temporal pattern an AI weather model uses to make a prediction was learned directly from this specific historical archive. Earth's climate is currently non-stationary. As global average temperatures increase, historical baseline data becomes less representative of future atmospheric states. If a neural network is forced to evaluate a severe meteorological event that has never occurred in its training data, it lacks the localized references required to map the outcome. To trust artificial intelligence for critical climate decisions, we must measure exactly how it behaves when it is forced to extrapolate past the hard boundaries of its known history. In statistical machine learning, encountering a data point far removed from the training set is known as being out of distribution, or OOD. Imagine a scatter plot of historical ERA5 temperature data forming a tight boundary, the training domain. Events inside are predicted by interpolating known points, but a heat wave 5 degrees beyond any historical maximum lands completely outside this established boundary. The model has never mapped spatial relationships at this extreme temperature. It has zero mathematical references to draw upon. For a neural network, a record-breaking extreme event is a literal mathematical blind spot. To quantify the impact of this blind spot, researchers recently published a targeted stress test in the journal Science Advances. They identified every instance during 2018 and 2020 that broke historical ERA5 records. They then evaluated the leading AI models, GraphCast, Pangu Weather, and Fuxi, exclusively on these unprecedented events. Performance was measured using root mean square error, or RMSE. In this metric, a lower score indicates a smaller deviation from reality, meaning a more accurate prediction. Standard benchmark evaluations test models against all weather conditions, meaning their results are heavily weighted by normal, highly interpolatable data. By isolating the extremes, this specific benchmark strips away the easy predictions to reveal the true structural limits of the models. This map shows out-of-distribution heat records globally. Looking at Panel C's overall data, AI models achieve lower error scores than the physics-based HRES, but restricted to record-breaking extremes in Panels D and E, HRES achieves superior accuracy compared to every AI. The physics-based HRES model maintains its reliability because fundamental thermodynamic laws apply with equal force regardless of historical precedent. Conversely, once the lead time pushes an AI model into an unmapped state, it exhausts its local regressors. Its forecasts revert to a baseline climatological distribution, containing zero predictive skill for the rare event. Physical laws scale seamlessly into unknown conditions, but pure data-driven models eventually hit a hard mathematical extrapolation barrier. As global temperatures rise, the baseline environment is actively shifting, pushing physical systems into entirely new states rapidly. Relying purely on a system trained on historical ER5 data makes a forecasting pipeline structurally blind to the physics actually driving a warming Earth. An AI model will mathematically regress toward historical averages, precisely when predicting an unprecedented extreme is most vital. Statisticians define this as the forecaster's dilemma, the trade-off between achieving highly accurate daily interpolations and maintaining reliable predictions for rare, catastrophic events. For policymakers attempting to manage physical climate risks, failing to anticipate these rare extremes carries massive socioeconomic consequences. A pure data-only approach achieves high computational speed, but it is structurally insufficient for protecting populations against novel climate signals. The objective for the next generation of climate research is to solve this extrapolation barrier, rather than abandoning machine learning entirely. One immediate approach involves using rigorous physics-based simulations to generate synthetic data for extreme events, artificially expanding the boundaries of the AI's training data. A more robust solution explicitly embeds the standard approach of thermodynamic laws directly into the neural network architectures themselves. By using physics to mathematically constrain the network's outputs, the AI is prevented from predicting physically impossible states, even when operating completely out of distribution. This hybrid architecture aims to marry the computational speed of data-driven interpolation with the reliability of physical extrapolation. The ultimate weather prediction system cannot rely entirely on memorizing the history of the Earth. It must explicitly calculate the laws of physics required to survive its future.